In this video, I'm going to talk about the gold foil experiment by Geiger, Marsden, and Rutherford. It will include details on the structure of an atom, which is needed for topic 7. This is common for both SL and HL in IB physics. At the end, there's some additional higher-only level material. So take a moment and read the success criteria for the video. Okay, so let's start with this idea. Why do we have so many names? Rutherford gold foil experiment, Geiger-Marsden gold foil experiment. Sometimes you hear one or the other. Well, basically, Geiger-Marsden were the ones that did the actual experiment. And then looking at that, Rutherford said, hey, you know what this is going to tell us? And Rutherford took it and did further calculations about the size of the atom and the nucleus. Okay, so let's take a look at what's happening here. So first of all, I have an alpha source. And I'm going to put it in a box, and remember, it's radiation. So that means it's going to be given off in all different directions. It's random, spontaneous, and we can't predict what's going on or where it's going to go. So what they've done is they've put it in a nice big lead box. You can see, and there's a small little opening here, which means the only alpha that's going to be able to leave this box is right here. And we're going to say it's collimated, which means it's only going to be able to travel in this direction, and so basically all of them are going to be parallel. Now they're going to be aimed at a piece of thin gold foil. That's important because it's a very malleable metal, and we can make it only a few atoms thick. So if it was a solid and we thought of the atom as a bunch of billiard balls, then when the alpha particles came here, they would knock off those gold atoms and they would bounce back. But what they actually found was the most of the alpha particles were actually detected right here. Well, actually even straight through. So what does that say? Well, somehow the alpha particle, and for those of you who don't remember, an alpha particle is 2 protons and 2 neutrons. So it has a positive charge. It's also not going to be very large compared to a gold nuclei. So since most of them went straight on through, that means the atom must be a lot of nothing. Now they had a few other things that went with this. So they did find a few that were farther over to the side. So somehow this collimated set of alpha particles coming out of our source got deflected a little bit. And the really weird thing is they found a few way back here. So in other words, a very small amount actually hit the target and bounced backwards. So here's a diagram showing particles leaving our source and how they might have interacted with the gold atoms. So here we have ones that are going straight on through, and we have some that are deflected. So you have to say to yourself, well, why would it be that some of these would be deflected, and perhaps even changing how much deflection would have occurred? So we said that alpha particles are 2 protons and 2 neutrons, so that gives them a positive charge. So in order to cause them to deflect like this, they must have been repelled. So what does that give us for information? Hey, the nucleus must have a positive charge. Since most of the particles went straight on through, we also can say then that this positive nucleus must be pretty small in comparison to the volume of the actual atom. So that leaves us to explain this one right here. Now, how would this alpha particle be bounced straight backwards? Well, first of all, not very common because that nucleus is such a small size. So the probability of hitting it isn't very likely. The other thing is that that alpha source or the alpha particle bounced straight back. It must be very light compared to the nucleus of the gold atom. Think of it as a child running down the hallway. If that child runs down the hallway and runs into an adult, they typically bounce right back off. But if they ran into another kid, the two of them go tumbling down to the ground. Okay, so it's then giving us some idea of what this atom must look like. Now remember I said that Rutherford went and did some calculations from this. So he used this idea of the closest approach. He tried to calculate then if we had an alpha particle with a certain amount of energy coming in, how close would it get to the nucleus? Again, with a positive charge, as you get closer and closer, the amount of repulsion gets larger and larger. We know that's an inverse square law. So then he calculated how close could you get. And his idea is then the closest you could get would then give us the idea of the size of the two atoms. So Rutherford calculated that the diameter of a nucleus would be around 10 to the power negative 15 meters, and the diameter of an atom being around 10 to the power minus 10 meters. So really small numbers, and you would find that the atom is 10 to the power 5 times larger than the nucleus. Quite a bit of a difference, which is why the atom is mostly empty space. Don't get caught. What's between the outside electrons and the nucleus? Nothing. Not air, not, some other particles. There's some electrons, but it's mostly just empty space. So what do the results tell us? Here's a summary. That the nucleus must have a positive charge. So it caused some repulsion, and that's how we got the small little deflections of some of the alpha particles. Most of the alpha particles don't even get anywhere near the nucleus, so that's why they went straight on through. And finally, because we only had a small amount of alpha particles actually bouncing backwards, that nuclei, which is very, very small, also must be very massive. Okay, so for the last little bit, that is HL only in section 12.2. Sometimes we get some deviations from what we see here. Earlier, I talked about the alpha particle coming in towards the nucleus and getting closer and closer, and because they're both positive, the electrostatic charge causes a force of repulsion, and it can only get so close. But the higher amount of energy the alpha particle has, the closer and closer it can get. And it might not be just that electrostatic force of repulsion that we need to consider. If you get close enough, you can get to the strong force. And if you remember, the strong force from topic 7.3 is what's holding the nucleus together. It's extremely strong, thus the name, but it only acts over a really short distance. And if your alpha particle is strong enough, you can get close enough to the nucleus that it will start making an effect. So the strong force is actually an attractive force rather than a repulsive force. So if the alpha has too much energy and gets too close, it's going to mess with our results. Later, in another part of the course, we're going to talk about electron diffraction, and that will actually be a much more accurate way to calculate the size of the nucleus and atom. So I hope that this has helped you, and you can now look at that success criteria and say, yes, I can do it.